Welcome to Minikun's Health Tutorials. In today's tutorial, we're going to learn about the concept of p-value in inferential statistics. But if this is your first time on my channel, please subscribe and let me know in the comments box below if you are doing a statistical related course. Without wasting my time, let's move ahead. So basically in statistics, we often have a lot of challenges studying a very big or large population. So because of this, statisticians came out with what we call inferential statistics, where instead of studying, let's say, a very large population that will demand a lot of resources, and besides, other challenges of studying a very large population include the unavailability of all members at a given point in time. Here's the case: we cannot stop the movement of people. So statisticians came out with the idea of rather doing what we call sampling or sample studies, where we will just create or make a sample of the original population, and then from the created sample, after, let's say, analyzing the created sample, we're going to infer or deduce the results of the actual population from our sample results. This is what we call inferential statistics. But the question is it all just easy as I've said? Let's say we just make a sample and then after which we deduce the results just as easy as I said? The answer is no. There is more to it, and we'll get to know that later. As you can see, we've already created our first sample, then this the second sample. In your own opinion, do these two samples resemble the original population perfectly? The answer is definitely no, and I would show you why. As you can see, in the original population, sorry, I'm trying to get a pointer. Okay, in the original population, as you can see, for instance, the probability of getting a blue ball in the original population is 5 on 12, and that of a red ball is 7 on 12. Now, with the first sample or sample A, you would realize that the probability of getting a blue ball is 3 on 12. Meanwhile, in the original population, this was 5 on 12. The probability of getting a red ball, okay, 3 on 12, that's equivalent to 1 on 4, yeah. Then that of a red ball is 3 on 4. But in the original population, that was 7 on 12. And then we let's try also, looking for the probabilities of either red ball or blue ball in the second sample. So we've made two samples out of the original population. With sample B, sorry, this is sample B, not A actually. I will correct it afterwards. You realize that in sample B, the results is absolutely okay. This resembles a little bit more because the probability of blue ball is 5 on 12 as in the original population, and the probability of a red ball is 7 on 12, which is pretty much the same as in the original population. But you realize that these two samples were randomly picked up or created from the original population, yet there is there's a high probability of one sample not resembling absolutely the original population. This is what we call sample fluctuation. So this sample fluctuation is actually the headache, or it's also termed as random error. That's, we just picked up the samples haphazardly, and then we have a high risk of either picking either more blue balls in one of the samples or in our sample. It doesn't mean in our studies we always study several samples. It's good. It increases the power of our analysis. We will get to learn that later on. But this basically what we call sample fluctuation. It's simply the fact that when we create different samples from a particular population, these samples are not going to, or each sample or any of the given sample is not gonna, there's a high probability that it's not actually going to resemble the original population. And when we look at these created samples, you realize that they are not also the same. For instance, comparing the two samples, they have different results. Probability of blue ball in sample A is 3 on 12, whereas probability of blue ball in sample B is 5 on 12. Likewise, probability of red ball in sample A is 3 on 4. Probability of red ball in sample B is 7 on 12. So this problem is what we call sample fluctuation. So what is actually the problem? What it means is that due to sample fluctuation, our sample will not always resemble our original population, and due to this, it means the results that we will obtain will not always be a true reflection of the original population due to random error or sampling error. And this leads us to what we call statistical hypothesis testing, where we gonna formulate hypotheses in support and against our results or our test or sample results, in a sense that if we assume that the results that we've obtained from our sample is actually representative enough of the actual population, then we're going to take into consideration the effect of sample sample fluctuation. In other words, the random error or the sample error. We need to take into consideration this. So we try to formulate hypotheses in support or against our results. We could have different types of hypothesis testings depending on our research question or the objective of our study. But all these hypothesis tests can be grouped into two. We have the one-tailed or the unilateral hypothesis test, and then the two-tailed or bilateral hypothesis test. You get to understand what is meant by one-tailed or two-tailed. It's simply with respect to the location of the critical value of the statistical test calculated. For example, be it a t-test or K2 or whatsoever statistical test, Fisher test or whatsoever, depending on where the critical values of the given calculated statistic will be located. If it's at the right side, then we call it a right-tailed or a superiority test. If it's at the left side, then we call it a left-tailed or an inferiority test. If it's at both sides, then it becomes a bilateral test. So it's all with respect to the location of the critical value on the probability distribution for the given statistic. But that's not, I wouldn't actually go into the details because the purpose of this video is to first of all give an introduction to inferential statistics. Maybe in subsequent videos I would give a detailed presentation or explanation of each test. But for the purpose of this video, let's move on. So the first example of a unilateral test is simply the superiority or the right-tailed test. What you should know is that the naming of any given hypothesis test is always with respect to the alternative hypothesis, which carries the difference that we are trying to prove. Remember, if we had done our studies on the whole population, let's say, or for instance, if we had studied the whole of population A and the whole of population B, and we came out with the population mean for A and the population mean for B, there wouldn't have been any need for hypothesis testing. But we are doing hypothesis testing simply because we carried out our studies on two different samples, which were randomly selected from the population. So due to this random selection, we have a risk of error, and that's why we term as random error or sampling error. This risk of error is what makes us, unable to actually conclude that, let's say, based on the sample results, in a sense that we didn't do our studies on the whole population. So we have to actually interpret our results taking into consideration the sample error. So we have to formulate hypothesis. We would look at, let's move on. We have the null hypothesis. So the alternative hypothesis is what we are actually trying to prove. In our initial, formulation, or in our research question, we are trying to say, okay, for instance, the mean age of population A is greater than the mean age of population B. In other words, the differences of the two means would be greater than 0. But if we had just done our studies on population, the whole of population A and the whole of population B, we could have just concluded based on our results. We don't even need to formulate this. If we look at the mean of population A from the calculated results to be greater than that of B, then we just say, okay, the mean of A is greater than B. But unfortunately, we did our studies on samples, randomly selected from both populations, in order to infer the actual means of, in order to infer whether, like, in the real population, or to deduce whether in the real population the average age of, let's say, population A is actually greater than that of population B. So because of this, we have to do hypothesis tests. So we formulate the alternative hypothesis in support of our research question, but it will only be proven right when the null hypothesis is unjust. In other words, it's not true or valid. So let's go on. So for instance, in the first example, we are saying mean age of population A. Mind you, we could do statistics tests for even percentages, for rates, for whatsoever. I just use mean to explain the principle. So let's move on. In inferiority test, we are trying to say the mean. So still based on the alternative hypothesis, what we are trying to say is that in inferiority, in other words, one-tailed, or sorry, that is a one-tailed test, of course, but a left-tailed. We are trying to say A is less than B. So we are trying to say, if we want, in other words, the differences between A and B would be 0. The difference between A and B would be 0. So the null hypothesis would be that the two means of the two populations would either be greater than or equal to 0. So if we move on, non-inferiority is an exception. Usually in statistics, you wouldn't hear of non-inferiority, especially in biostatistics or other statistics. You only hear of superiority, inferiority, and then bilateral or inequality test. Hardly do you hear of non-inferiority, equivalence, but it doesn't mean, that's why I'm trying to say the hypotheses are actually formulated with regards to what we are trying to prove. These are not fixed, or it's not like it could be twisted anyway. In statistics, we only try to criticize, but in clinical research, we try to formulate hypotheses in favor of the pharmaceutical laboratory. That's why in clinical research, we don't have anything like inferiority test, but we have rather non-inferiority, where we are trying to say, for instance, let me use a pointer, please. where we are trying to say, for instance, treatment A is not worse than treatment B. In other words, we are trying to say treatment A, we've accepted that treatment A is less than treatment B, but not to some extent. So we are trying to say the differences between, even though treatment A is less than treatment B, the differences between treatment A and B should be greater than a particular what should I say, margin. It should not be more than, the differences should be more than, sorry, minus I don't know what to call it, minus margin, let's put it that way, minus inferiority, non-inferiority margin. That's to say, for instance, if we are trying to say, for instance, the differences between treatment A and treatment B in terms of efficiency must not be less than or -5, even though we've accepted that treatment A is less than treatment B, or in other words, we've accepted that treatment A is worse than treatment B, but the differences mustn't be less than a particular given margin. So this, you would only hear this in clinical research, but it's all part of statistics. That's why. So the null hypothesis would be that, okay, treatment A, in other words, the differences between treatment A and then treatment B should be less than or equal to, that's the opposite of the alternative hypothesis. It should be less than or equal to the non-inferiority margin that we've already defined. So with a two-tailed or bilateral hypothesis test, we would look at, first of all, the inequality test. So as I said, the name comes from our research question. In other words, the alternative hypothesis that we are trying to study in the population using samples coming from those particular populations. It's not always all about comparing two or more populations, and sometimes we just want to compare a particular population, or what should I say, the sample results to the referential, in other words, the theoretical or the actual population. For instance, if we could do our studies on a particular given sample, and we try to infer or deduce the actual value of the real population from our sample results. So sometimes we try to just compare our sample results to the actual population results. So it's not always all about, let's say, comparing A or B. That was just to throw more light. But let's look at the inequality test, for instance. We are trying to say A is not equal to B. In other words, the differences between the mean age of, let's say, population A would not be equal to 0. So it could be less than or it could be greater than. So you see that the null hypothesis would be that the two populations have equal means. So, but first of all, we would actually prove that there is a difference, or in other words, we would actually accept the alternative hypothesis, which is in favor of our research question, only if the null hypothesis is true. To conclude that the null hypothesis is true, you would have to take into consideration, you would have to conclude at a risk due to sample error. Like, you cannot just, so this is a whole lot. I don't want to really go into the details, but right now we just try to understand the principle of inferential statistics. Now, we could also have with another bilateral test that we call equivalence or two-sided test. This also comes from clinical research or in epidemiology. We don't have this. It's not like, it's not all that we are trying to, whether clinical, epidemiology, whatsoever, it's all part of statistics or biostatistics. As I said, these hypotheses are not fixed. It depends on your research question. But I just try to, that's why I've decided to add non-inferiority and then equivalence trials. But in our biostatistics books, most of the time you find superiority, inferiority, and then two-sided. Why? For instance, if assume that you are the pharmaceutical laboratory or the manager of the pharmaceutical laboratory, I don't think you would want to prove that, let's say, your new treatment, which is, for instance, treatment A, is let's say this is actually where we are. This is the objective. This is the alternative hypothesis. So I don't think you would try to say your new treatment is inferior than the existing or the standard treatment. Then why would you have to waste time fabricating or this particular drug just to prove that, or just to fabricate a drug that would be inferior than the existing drug? It wouldn't make sense. But you would, that's why, but in actually in class in statistics, statisticians are there to criticize, so they could formulate any hypothesis based on the results, but for different purposes or different industries, they have their objective is always to make something that is better than the existing treatment. So for instance, in clinical research, the pharmaceutical laboratory would, even if they know that maybe the new treatment is lesser than the existing, is worse than the existing treatment, but they would try to give a particular margin. They would say, okay, maybe we would have to say, okay, maybe we accept that the new treatment might be worse than the existing treatment, but the difference shouldn't be less than a particular given margin. So that if the alternative hypothesis is true, people will still buy the drug, in a sense that the new treatment is not worse than the treatment A, and probably the new treatment has other advantages, like, maybe it's easier to be I don't know, it's easily administered. It's not having, let's say, a lot of side effects and what have you, compared to the existing treatment. So you would agree that, okay, why don't we accept to lose, let's say, some extent of efficiency, let's say, to have a drug that would be, let's say, easily, that wouldn't have a lot of side effects. So it's almost like economics. There's like opportunity cost. If I agree that, okay, I would lose, for instance, -5 of efficiency to produce a drug that wouldn't be worse than the existing treatment, but that would give other benefits, that maybe the existing treatment cannot give. So these are the kind of hypotheses. We have all different kinds of hypotheses, but they are all formulated depending on the objective of our study or research. So, for instance, in equivalence study, we are trying to say, okay, treatment A is worse than, it should not, even if treatment A or the new treatment is worse than treatment B, but the difference shouldn't be lesser than, or in other words, the difference should be greater than a particular margin, which is negative, let's say non-inferiority, or a negative, let's say, equivalence margin. Like you could say, for instance, -5. We've agreed that, okay, even if A should be less than, that's the difference. The actual differences between the existing treatment, which is B, and then the new treatment, which is A. Or you could invert it as you like. Even if the difference, even if, let's say, the new treatment is worse than the existing treatment, but the difference should not be less than a particular margin. So in other words, it should be greater than this particular margin. This is actually the difference, the sample difference, and this is the margin, the predefined or the prefixed margin. And if let's say this particular drug should be more effective than the existing drug, but its effectiveness should not also, surpass a particular margin. Like, in other words, that's this actually the upper boundary of our interval. This so the why would we say it shouldn't be so efficient than let's say to some extent compared to the existing treatment, simply because for instance in anesthesiology, if a is too, let's say, let me put it in quotes, powerful, the patient may never wake up after taking it. You understand? After the surgery, he would just die. So we try to control everything. So you see, in actual, what should I say, in real life, the hypothesis tests are usually formulated to suit the purpose of the study. In textbooks, you would see that in biostatistics, they'll be talking about right-tailed or superiority test. They will definitely talk about inferiority or inequality test, but hardly do they talk about non-inferiority or equivalence test. But in clinical trials, we have them. That's why I decided to add. But all that we are discussing is part of statistics. So in clinical trials, we could have superiority test where we will try to say, okay, drug A is or the new drug will be better than the existing drug, or we would have a non-inferiority or equivalence trials or tests. Inferential statistics comes in two categories. In the first category, we are trying to compare a sample value to a theoretical value. In other words, to a population value. For example, we've calculated the mean age of, let's say the average temperature. For example, we've calculated the average temperature of patients suffering from a particular disease, and we try to compare our results to, let's say, the norms. Probably we carried out an intervention, and we try to compare our results to the norms. Let's say, for example, after the administration of a particular drug, the temperature is supposed to decrease to a particular level. So, and then we know the actual norms or intervals, the theoretical intervals. We have done our study and we try to compare the results. So we are actually trying to compare the average mean of our sample to the average mean of the real population. If we had done our studies on all the number of patients suffering from this disease, if we had administered this drug to all of them. So in this case, we are simply comparing our sample mean to the actual population mean. And in statistics, please let me use the pointer. We often represent, let's say, the sample mean by small m, and mu to represent the population mean. But it's not just all about mean. I'm just using mean as an example. We could have been comparing maybe the standard deviation of our sample, or another different statistical parameter. It could be a percentage of our sample to the percentage of the population. It depends. So generally, in the alternative hypothesis, which is our research question, in fact, we are trying to say that there is a possible difference between them, but we cannot boldly say there's actually a difference, in a sense that we didn't study the whole population, and due to sample fluctuation, we cannot go ahead and say this. So we have to say, okay, this is our research question. There's a difference, but we have to consider the opposite. That gives us our null hypothesis, where we would say there is no difference, but at a particular risk, because there could still be a difference, and that's why we say risk alpha. This risk alpha is due to sample fluctuation. So this risk alpha is actually in support of the alternative hypothesis. Let's move on. In the second category, we are trying to compare different sample population results using samples from these particular populations. For example, we want to study, I don't know, let's say we want to compare the mean ages of population A or population 1 and population 2. Let's say the population, let's say African population and then maybe European population. We are trying to compare the two. Let's say the average age of, let's say, European population and then African population. We definitely not gonna be able to study the entire African population and the entire European population. So we're gonna have two samples. Sample 1 is European, sample 2 is African, for example. And then after we've gotten our results, we try to know whether in, let's say, the results that we've obtained, provided the samples were actually representative of these two populations, do we have the right to extrapolate our results to say, okay, we've done our studies on these two samples, and then in the actual European and African population, the average age of a man is maybe 25 years in Europe, and that of maybe a man in Africa is maybe 55. Can we boldly say this to say, okay, there is a difference between these two ages? We can't say so because we didn't state the entire population. So we have to consider the fact that sample fluctuation had its role in the results that we've obtained. So we cannot conclude exactly. That's why we need to formulate this actual research question. There is a difference, a possible difference for that matter. The null hypothesis would say there's no difference. And at what risk are we saying there's no difference? Where we give alpha, which is due to sample error. Now, I think I've already answered the question, but in your own opinion, how are we gonna solve this problem? Like, how are we gonna take into consideration the alpha error or the sample error to enable us actually extrapolate our results, like without any hesitation, to say, okay, from the sample results that we've obtained, let's say in case we are comparing a sample value to a theoretical value, are they not equal or are they equal? What would permit us to say so? Because we haven't studied the whole population. Or if we are comparing different population means, this is actually the population mean, so we will calculate, we will deduce this from the sample means, which will be M1 and M2. Here is different. We are comparing a sample mean to a population mean. What would permit us to do this? So statisticians came out with the idea that, okay, we would study, let's say, the distribution of populations and start to, so they decided to, they couldn't even study, it was still the same, game, just as we do our studies. It's not like they studied the entire population. No, they still brought, but what they did was that they made different samples so that to confirm their results. So they made different samples and they measured different statistical parameters. For example, they started to measure, let's say, mean, and then they decided, okay, we're gonna make different samples measuring mean, for example, in different populations, in different scenarios, and then or design statistics, let's say study designs, and they realized that, okay, they decided that, okay, with a particular given sample size, and then let's say, which will be, let's say, the degrees of freedom actually is actually calculated from, let's say, with a particular given sample size, which will give us a number of degrees of freedom. This is the nature of the distribution of the population of this particular sample, or the population from which we drew this particular sample. So they took into consideration the sample size and what do we call it, the fact that there will be sample fluctuation. So they fixed alpha, which is the sample error due to sample fluctuation. Said, okay, this is always the nature of the distribution, and they decided, okay, why can't we represent the distribution of a population by, let's say, a statistical value which will permit us to, let's say, so they came out with the idea of, let's say, I'm using t-test here simply because this is actually, we are talking about comparison of mean, but I said it could have been comparison of percentages, it could have been any other comparison, standard deviations or whatsoever. So, but at the meantime, let's just talk about t-test since we are talking about means. So they've given, let's say, they realized, okay, with what do we do to represent the distribution of a particular population or a particular the distribution of a particular population, considering the sample difference. This is actually the sample difference. For example, if it's mean, this is a distribution of, so they came out with the fact that, okay, the distribution of the population would be a function of the sample difference that we've observed from the population results. In other words, this distribution here, which we represent as T alpha, is simply a function of the sample results and then the true population results. And this will be true. It means, what it simply means is that taking into consideration the distribution of the sample and then the number of degrees of freedom, in other words, the sample size, the sample distribution will be equal to the population distribution, but at a particular risk due to sample error, which we usually fix at 0.05. So we are 95% sure, in other words, the probability of this being true, that the distribution of the population would be equal to the distribution of the sample, taking into consideration other variables like the variance and what have you. That's why we say distribution of population is a function of the difference between the sample difference from the population. Would be 0. We will be 95% sure, and the rest of it, that's 1 minus, or in other words, 100% minus 95%, or if you want in probability, 1 minus 0.95 would be 0.05. So we attribute this 0.05, which is left, to the fact that we cannot boldly say the null hypothesis is true. Like, there's no difference. The distribution of the sample is equal to the distribution of the population. We cannot boldly say so because of sample error, but we have already presumed or that, okay, we would give a particular probability. So alpha is not always fixed at 0.05. It depends on the test conditions. You could increase it. For example, if you have a very large sample size, you would decrease your alpha, and especially if, let's say, you are carrying out several studies, let's say multiple studies for the same what should I say, to prove the same thing, to prove that maybe M1 is equal to M2. Since you are carrying multiple studies, you're gonna divide, let's say, this alpha by the number of studies that you are going to do. Or sometimes if you have a what do we call it, a judgment criteria that is multiple, like it is composed of different parameters, let's say different judgment criteria combined together, you'd need to divide, or in other way, to minimize your alpha. So there are a whole lot of, so just to tell, this was just to tell you that alpha is not always 0.05, but this is how it is. And now, as you can see, so what it means is that with knowing, let's say, the sample size and then the alpha that we've already fixed, so if we can deduce the theoretical statistic distribution of our sample per the rules of these statisticians, this is not like magic. All that we get, the T alpha, is simply with respect to their rules. They came out with the fact that, okay, with a particular given size of this, and if we assume that the random error would be this, then considering this difference, the sample difference, they say of whatever parameter, if it's different, the difference of the sample mean, for example, from the population mean, then we would say that, okay, the distribution of the sample, or in other words, the actual population, which will be a function of the difference, would be equal, like the sample distribution will be equal to the population distribution. But at what risk would we be saying this? So this is actually the null hypothesis here. So right now, if we know, let's say before we even start the test, we've already known our number of the sample size, and we've already known alpha, then what it means is that we can also calculate our degrees of freedom. And what it means is that we can find this distribution. In other words, just a value that represents the statistic value. Is simply a value representing the distribution of the population, taking into consideration the differences between the sample and then that of the population. So for instance, if alpha is 0.05, implies 95, confidence level will be 95, for example. And then you can find, it depends on whether it's also one-tailed or two-tailed, it depends. So you can find that we've already looked at, whether one-tailed, superiority or inferiority, as I said, depends on the objective of the study. We could have said, let's say, we could have said maybe M1 is greater than, or in other words, not M1, the sample population is greater than the population, the sample mean is greater than the population mean. This could have been our research question. And then the null hypothesis would be that the sample mean is less than or equal to the population mean, so it's not always fixed. So what happens? What it means is that we can get this critical value, which will be the what do we call it? The distribution, which will be the presumed population distribution based on the standards of these statisticians. But now, since we are working on a sample, we will need to also calculate the observed, that's the actual sample distribution, taking into consideration our sample size, which will be the same as this theoretical sample distribution or population distribution. But this time around, we're going to take into consideration the sample results, that is the mean of our sample. So let's say in the case where we are comparing the sample means to a theoretical mean, then this how this difference will be like this. In the case where we are comparing the two or more different populations, in this case, let's say two means, it's not always mean, as I said, it could be percentage, but I just use t-test because we are talking about means. In this case, we would use our sample mean so that we can the differences, so that we can calculate our observed statistic. So as I said, you would realize that observed statistic, which represents the sample distribution, will simply be a function of what? The difference here. But this with respect to the sample. This one was with respect to the same sample, but compared to, let's say, a population, a theoretical population that's in the actual population pertaining to their studies. So at the end of the day, we can also calculate what? The observed statistic. So this observed statistic is just like a model, let's put it that way. It's a statistical model that we are comparing to the theoretical model. So we expect that everything for, let's say, the null hypothesis to be true, what it means is that the observed statistic must be the same as the theoretical statistic, considering our sample size. In other words, P here is playing the same role, which is a p-value. It's actually playing the same role as alpha. What is P here? P simply here is the probability of the null hypothesis being not what should I say, not being true due to a random sampling error. Just alpha is playing the same role. Alpha is also the probability of the null hypothesis not still being true due to what random sampling error. But the problem is that this here is a theoretical statistics that we or a theoretical model based on the statistician's observation. They have already fixed their probability of this not being true, of the null hypothesis not being true. In other words, the distribution of the sample not being equal to the distribution of the population. In other words, this actual distribution of the sample not being equal to the distribution of the population. They have already done that. They have fixed their probability to be this. So we have worked on our sample. We couldn't have fixed a probability in a sense that we don't know our results. Would it be due to sample? Even if at all there is a difference, would it be due to what do we call it, sample fluctuation? Or assuming, let's say, we had administered some drugs to, let's say, population A and population B, could it could this difference that we've observed have been due to the fact that we administered those drugs? Like, in other words, the difference, is it statistically significant, or it's not it's not significant, is it? So for that matter, we cannot give this probability. So by what we do is that we know that we can calculate our observed statistic. So from this formula, so when we get our observed statistic, and then with our number of degrees of freedom, knowing that we also know our sample size, then we will be able to deduce this probability. And then we now compare this probability. So let's assume the degrees of freedom is set 7. And then what do we call it? Our statistic that we've obtained is 1.89. Now we would just trace here to get our alpha. These results were obtained from those, statisticians. They studied different samples from different populations with respect to, let's say, the mean. So that's why we have, let's say, if it's Q2 test, for example, if it's for percentages, then we have the Q2 table. That's to say, when they study different populations using different sample, let's say they try to compare different percentages, sample percentage and then population percentage, and they came out with how it's supposed to be theoretically, knowing, let's say, the only difference is that in our case, we have the statisticians theoretically, they always assign alpha to be 0.05, or it could vary, as I said, depending on the type of study. If, let's say, like the number of, if we have a lot of the sample size is large, then what it means that it's a true representation of the population, and in that sense we would decrease the risk of error due to hazard, or let's say random error. We would decrease it. So that's how it is. So we would, by calculating the observed statistic and then knowing the degrees of freedom, we can also find our p-value. But here we cannot, it's sometimes hard to deduce the exact p-value from the table. And mind you, this is just to explain, if not in actual sense, we don't need any of these tables. Like, we just, statistical tools to help us, like R, there's Excel, you can do t-test anywhere. So what it means is that this difference here is simply what we call it, the difference that you can see as in the formula, be it anything, any comparison, it could have been percentages or whatever, so whatsoever, is what I've represented as this change observed. So that's between samples. If you are to compare different populations, then it means we will compare the change in the samples, and that will help us get a statistic for us to get our p-value. Then we will now compare. if it is comparing a sample value to a population value, there's still a difference between a population. So what it means is that the observed statistic is simply a function of this difference, taking into consideration the standard deviation, the sample size, and other parameters. So now I've made you understand that this model is the same as this model. The only difference is that this has been defined. That's just the norm to say, okay, if we assign the probability of this being, I don't need to repeat that. So if what it means that this model is just the same as this, if we come out with a probability of these results being due to what do we call it? What it means is that this model still explains our null hypothesis just as the theoretical model explains. The theoretical model explains that the distribution of the sample is the same as the distribution of the population at 95% level of confidence. The 5% is due to sample error. And that 5% is in support of the alternative hypothesis. That's to say, if really the sample distribution is the same as the population distribution, then the only risk of error, in other words, the only risk of it not being true, in other words, of the alternative, the opposite happening, would just be attributed to sample error. We would say, okay, we cannot boldly say the distribution of the sample is the same as, the population is the same as the distribution of the sample, simply because there is a 5% risk of error that they might not be the same due to sample fluctuation. So alpha is actually in support of the alternative hypothesis and not the null hypothesis. So when we write alpha against null hypothesis, we are only trying to say that at what risk are we saying that, okay, there's no difference. In other words, the null hypothesis is true. So that's why when the probability of the observed statistic, in other words, the probability of the observed distribution being equal to, let's say, let me reformulate this. That's why in a case where this pertaining to the sample, this also representing the population distribution, considering our sample size, and then the, what do we call it? Yes, considering our sample size and the variation, in other words, the variance, and then the distribution of the population of the samples, considering the variation of the sample and then the number of the sample size. This also represents our population distribution. This also represents our population distribution, but this is the norm, in a sense that alpha has been already defined. Our alpha here represents P. So if our alpha, and then alpha is known to be the probability of the null hypothesis being true, in other words, distribution of the sample being equal to the population, or you could say the population distribution being equal to the sample distribution. So what it means is that if we come out with the probability here, in other words, p-value being greater than or equal to 0.05, then we would say that the difference that we've observed, the sample difference, is the same as the difference in the population. That's to say, the distribution of the population is the same as that of the sample, because it means whatever difference that we've observed physically is just due to what? Random sample error, in the sense that the probability of random sample error is equal to the theoretical probability, which is alpha, or even more. But in the case where p-value is less than the norm, which is alpha, then what it means is that the results that if there's actually a difference, then there's something that is responsible for this difference, and not due to sample error. Because if it were due to sample error, then we would have had a larger probability of sample error, which is p, compared to alpha. So now let's try to see how to conclude a statistical test. Assuming we are to conclude this right-tailed statistical test, how do we conclude? Basically, there are different ways of concluding. On the basis of the p-value, you could conclude on the basis of, let me use a pointer. On the basis of p-value and then alpha, we could make our conclusion. Also on the basis of the observed statistic and then the theoretical statistic, we can still conclude. In some cases, we even use intervals with a given confidence level. So there are different ways to conclude. So given this example, how do we conclude? As you can see, in your own opinion, would you say, the difference between, let's assume we are still comparing sample mean to population mean, or different population means, and this is the graphical representation of the test results. This is a t-test for that matter. So as you can see, this axis represents the differences in statistical value. At 0, what it means is that there's no difference at all. The difference is 0. In other words, the sample mean would be equal to the population mean at 0. So statisticians after they did their test, they came out with the idea that, okay, if we are comparing means and then we make a sample of size n, and then we assume that the probability of this sample size, the probability, assuming the distribution of the sample is similar or equal to the distribution of the population, then what it means is that any results that we obtain on a sample will be the same as that of the population. It will be a true reflection of the population at just a risk of 0.05. So it means 0.05 is the only probability where the sample distribution would not be equal to the population distribution due to sample fluctuation or random sample error. Then what it means is that the only difference would be between 0 and then alpha. Theoretically, if there's nothing that is if there's not any extra influence, for example, maybe we have carried out an intervention, we've administered drugs or something, and that has made a change in the parameter, and in this case the mean that we are measuring. If we haven't done anything, or if what we have done is not effective, if we try to make any change and the change is not effective, then what it means is that this difference here, the difference would not be significant. It will just be a reflection of the sample error. So what it means is that at 0 there is no change in what we call a statistical value, or in other words, distribution between the population and then the sample. So they said, okay, given a particular given sample, this is how it's supposed to be. The only difference would be from 0 to the statistical value alpha, taking into consideration the variance or the standard deviation of the sample, and then the degrees of freedom, in other words, the sample size. This is the difference between, at 0, as I said, it means there's no difference between the sample population value and then the sample value and then the population value. In other words, the population mean, the sample mean, at 0 there's no difference. But due to sample fluctuation, the difference would be between 0 and then t alpha, in other words, the theoretical statistical value, and that difference is due to alpha, which is sample error. Now, in a case where we decided to do our studies on our sample, this is how our sample was supposed to be. But we cannot fix a probability of 0.05 because we have carried out an intervention on our sample. Probably we injected a patient, or we did something like that influenced or that accounted for the increase in mean age, for example. So we cannot fix that probability, and that's why we are doing our test to know in case the intervention that we carried out never had an effect, then it means the only probability of the change that we observe between our sample values would only be due to the random sample error. But in case something happens, then it means the probability of our sample, what do we call it, the difference that we've observed being due to random sample error would be what, less than the natural or the random sample error, to tell us that okay, the result that we've obtained is not actually due to random sample error, because the probability of it being due to random sample error is lesser than the normal probability, that was like the normal, in other words alpha, theoretically. But in this case, as you can see, we've realized that p is actually greater than the alpha. That's to say there's more probability that the result that we've obtained would be due to random sample error, even if at all there's a difference. In the real population, there will be a higher probability of the results that we've obtained being due to random sample error. So as you can see, that's why I use different inks. This blue portion represents alpha, and then the whole of this green portion, including the blue portion, represents p. So what can we say after all that I've said? What would be our conclusion? Obviously, we could conclude that there is no significant difference on the basis of the p-value, in a sense that the p-value is actually greater than the p-value. When we talk of the p-value, it's all about the surface. That's the surface, that's the probability distribution. We are talking about the surface here. The distribution of the statistical test, t-test, is all about the surface. So as you can see, the p-value, that probability actually covers the whole of this, and then alpha is just this. So it means p-value is actually greater than this. That's why I use, you could see that even here, you see that there's a mixture of the shading to tell you that p actually covers the whole of this, but alpha is only the blue region. So if p is greater than alpha, then it means we have to accept not to accept, you get to know why, but we would definitely fail to reject the null hypothesis. Rejection of null hypothesis doesn't mean we are accepting it, in a sense that probably there might be a difference, that is statistically significant, but we couldn't what should I say, we couldn't prove this difference by our test results, maybe due to lack of test power. Our test power wasn't sufficient enough to prove this difference, probably due to small sample size, or I don't know, maybe other errors or biases. So for that matter, when we fail to reject the null hypothesis, it doesn't mean we've accepted, but we say we cannot affirm or we cannot conclude that there is a statistically significant difference between the actual population results that we are trying to infer or deduce from the sample results. So that's just one way of concluding on the basis of p-value. When p-value is greater than alpha, then we would say there's no significant difference in the population. So as you can see, as I said, at 0, there's no difference between sample population, what do we call it, sample, the sample value and then the population value. But with at what do we call it, at t alpha, this difference is due to alpha, or the random sample error. Now look at our observed difference. The observed difference is the difference between the zero region or the 0 point where there's no difference between the sample error and then wherever the value that our statistical value has given us, our test statistics or observed statistical value is. So that's between 0 and this. So what can we say based on this? What it means is that when the difference between or when the observed statistical value is small, then what it means is that we would have a small, if the observed difference that's between our sample values that we let's say m1 minus m2, if that difference is small, then what it means is that, in other words, right now we are inferring the true population. So we would say if mu1 minus mu2, if that difference is actually minute, then what it means is that it will give us a small statistical value or observed statistical value, as we've seen, compared to the difference here. You would see that this is small, the observed change or difference is small. Then at that point, as I said, you realize that the observed statistical value becomes smaller than the theoretical statistical value for our sample distribution. So at that point, we can just conclude that there is no significant difference. But maybe if we want to conclude with a p-value, definitely due to this, what will happen? P-value will increase, as you have seen, because if t decreases and then it becomes less than t alpha, t o or t observed t decreases and it becomes less than alpha, what happens? It means the observed statistical value is actually inversely proportional to the p-value. You see that when it decreased, what happens? The p-value increases. And when the p-value increases, it becomes what? Greater than alpha. When it's greater than alpha, what it simply means is that there's a greater chance of the test results being due to what? Random sample error. Remember, p-value is the same as alpha. I would explain why I said so. P-value is the same as alpha in the sense that they are playing the same role. So p-value is actually the observed random sample error probability, and then alpha is a prefix or predefined, or it's a norm. That's to say, if there's no difference at all, if there's no any change either than the random sample error, then the risk of the null hypothesis not being true would be what? Alpha. P-value plays the same role on our observed sample statistic. Also in support of the alternative hypothesis, but against what? The null hypothesis, to say, okay, based on our sample, or what should I say, our observed distribution according to the sample results, for our results to actually, for the null hypothesis to be true, that's to say, if there's no difference, then the probability of this, let's say, of any difference would actually be due to sample error. So we are comparing this model, which is the observed model from our sample, to a theoretical model. So everything, as we showed you earlier on, everything here is the same as this. But so right now, let's say in the case where there's no difference, this has to be the same as this. So we are comparing. It means p-value is the same as this, as alpha. In terms of roles, they are playing the same role. So when we realize that, okay, our observed value, that this real, this theoretical. So if the real thing is the real probability of random sample error is actually greater than the hypothetical probability sample error, then what it means is that there's more probability that the observed results would be due to what? Or the observed change here would be due to random sample error. And we have every right to say that there's no significant differences between the population results, and even if at all there's a difference, it's due to random sample error. That's what it means. So we would say there is no significant difference between, let's say, the sample mean and the population mean, or the two or more different population means that we are comparing. Let's look at the second scenario. What would you say? As you can see, it's directly opposite to what we've already discussed. Obviously, our p-value is less than alpha, as you can see. This is just the region of p. This is the same concept, so I will not repeat by saying, okay, alpha represents the probability of the null hypothesis not being true due to random sample error. That's to say, alpha is in support of the alternative hypothesis. To say in a real population, if there's no difference between what we are comparing, whether it's mean of population 1 to mean of population 2, if this is really true, then the only probability of this not being true, in other words, the alternative hypothesis being true, would just be due to the random sample error, which is alpha. And that probability of random sample error is alpha. So in other words, we have what our confidence level is 95%. In other words, 1 minus 0.05, and that gives us a probability of what 0.95 if the null hypothesis is going to be true. So in this zone, if the observed statistic falls within this zone, then what it means is that we are not going to reject the null hypothesis, as we've shown here. It observed, but here you can see that the observed statistical value is actually greater than the theoretical value. And because it's greater, as I said earlier on, when t increases, what happens? P-value decreases. So when p-value decreases, what happens? P becomes less than alpha. And when p is less than alpha, what it means is that we are trying to say the probability of the observed difference, if let's say in a real population, the probability of the observed difference being due to random sample error is actually less than the prefixed probability. So that in this difference must be accounted for by something, by a particular change other than random sample error. So at that point, we can say the difference is significant. So if the difference is significant, then we have to reject the null hypothesis, which is saying that the difference is insignificant at a risk of 0.05. So you would conclude that the sample mean, in other words, we would reject the null hypothesis, and by rejecting the null hypothesis, then we accept the alternative hypothesis by saying that the difference is statistically significant. To say the sample mean is not equal to what the population mean, or in the case where we are comparing two or more populations, the mean of population A or 1 is not the same as that of population 2. It's not all about equal to or less than, but as I said, I keep on repeating it. It depends on our initial formulation, depends on the objective of our research, and it depends. We could have said maybe sample mean is less than population mean, and then in that case, the null hypothesis would be what? This is actually our research question. This is what we tried, the difference we tried to prove. Then our alternative hypothesis would have been that since we said this is less than this, then this would either be greater than or equal to this. But that's why I was saying superiority, inferiority, or whatsoever test, it depends on what we are trying to, our objective of the test or the study that we are doing. So as you can see, the observed theoretical difference, considering our sample size, and then the fixing the alpha, in other words, the probability that the difference will be due to random sample error, to be 0.05 if the null hypothesis is true. This is what the difference represents. That's from 0, as I said, there's no difference between the observed sample and then the population's the observed value, in other words, the observed mean and then the population mean at 0, there's no difference. The population mean, if you create a sample from a population, provided the distribution is the same as that of the population, it means the test results will be the same as that of the population. And what it means is that there won't be any difference. This is a difference in actual statistical value. This is a difference. The horizontal axis represents the difference in statistical value. So here there's no difference, that's 0. But due to random sample error, which is alpha, there's a probability that of 0.05 that there could be this difference, and this difference here is accounted by the random sampling that we did. That probability is 0.05. So that probability is the whole of this region right from here. So in this region we cannot reject the null hypothesis. From here we can reject the null hypothesis if our observed statistic falls within this region. And as you can see, observed statistics is in this region. In other words, is superior to the theoretical statistical value. And when it's superior to this, remember I said observed statistics is inversely proportional to the p-value. When it's superior, it means when it increases, what happens? P-value decreases. And what it means that when p-value decreases, then it means we have a lesser probability of the observed difference being due to a random sample error. We have a lesser probability. Then it means there's something that might have, compared to the prefix or the predefined random sample error. So what it means is that the difference is statistically significant, or that's to say something, if for instance we carried out an intervention, we gave treatment, then probably that difference is due to the treatment and not random sample error. So as you can see, if the observed difference is greater than the theoretical difference, then it means there's something that's responsible for this difference here. So when this observed difference increases, what happens? We have a greater statistical value, and then the greater statistical value, that's to say the observed statistical value would be what? Greater than the theoretical statistical value. Then since observed statistical value is inversely proportional to the p-value, it means there's what? Lesser chance of that's to say if this difference is very large, then what it means is that there's something that's actually responsible for this difference, either than the what do we call it, the random sample error. So what happens? The probability of random sample error would decrease, that is p here, compared to alpha. So hence p will be less than what? Alpha. And then our conclusion is that there is a significant statistical difference between those two or more parameters that we are comparing. In this case, it is because we base all my explanation on mean, then in this case we are trying to say there's a significant difference between the sample mean and the population mean, or the mean of population A or population 1 and then mean of population B, based on the inferences that we've made from our sample studies by calculating what? The observed statistic, which is TO. Thanks for watching, and please subscribe.